What is going on, guys? Welcome back to the Python data structures tutorial series. In this video today, we're going to implement the heap data structure. So let us get right into it. Alright, so we're going to implement the heap data structure from scratch in Python today, and as always I want to start by giving you guys a little bit of a theoretical understanding of the data structure before we get into coding. And a heap is a tree-based data structure similar to the binary search trees that we talked about last time, but it has different properties, different operations, and also different use cases. So in a heap, first of all, we have two different types. We have a min-heap or a max-heap, and depending on that, the order is reversed. But basically we have a top element, which is either the minimum or the maximum of the data structure. So for example, if it's 10, all the values below 10, so all the values in the nodes below this top node here in a min heap would be larger than 10. So for example, they could be something like 20, 30, 40, 60, 50, 35, whatever, it doesn't really matter, but all these values are larger than 10. So the minimum element is always at the top. And this is, by the way, true. If this is a heap, if this is a min heap, then all the subtrees here are also min heaps. So you can see that 30 is smaller than 50 and 35, and 20 is smaller than 40 and 60. So all the subtrees in a heap are also heaps. And if it's a max heap, it's the other way around. So it would be, for example, 5, 3, 2, 1. I mean, if we allow for duplicate elements, we could also have 3 here. But we basically have the structure that the topmost element of each heap, so also of the sub heaps here, has to be either the largest or the smallest element. So it's not like in a binary search tree where everything to the left is less than and everything to the right is greater than the value, but everything below this node has to be larger or smaller than the value that we're talking about, depending on whether it's a min heap or a max heap. And this is very useful to implement a data type, an abstract data type, which is called the priority queue. Now, the priority queue itself is not a data structure. So it is a thing, an abstract data type that can be implemented very efficiently using a heap. So basically the element with the highest priority or with the lowest priority would be at the top, and then we could just get the next most important element. And for this, we basically have two operations that are important. For example, if I have now here again 20 and 30, and then maybe I have 25 and 40, and then maybe I have 50 and 32 or something like this. How a heap works, how a min heap works in this case, is I can extract, this is the method, I can extract the minimum of this min heap. So I would get 10 out of the heap. I would process it if it's a priority queue, for example. And then what happens is I remove this node. So I don't have the root node anymore. I don't have the top node anymore. So what do I do in a heap? What I do is I take the last element. We're going to talk about what last means in a second here. I'm going to show you how this works in terms of calculation, because we're actually basing all of this around an array full of values. And the indices determine which node or which value is the child of which other value. We're going to talk about this here in a second. But basically what we do is we remove the top node, then we take the last node, we put it at the top. So we basically take the last node here, we remove it from the end, we put it at the top, and now this is of course an invalid heap. This is no longer a min heap. And what we do is we do a so-called sift down operation, which means that we look at the two child nodes and we determine which one is the smallest. So in this case, 20 is the smallest of these three. So we swap the position with 20. And in this case, what would happen is we would get 20 up here and 32 down here. And then we look again, okay, what's the smallest one of these three? We see it's 25. So we replace 25 with 32 and vice versa. And now this is a valid min-heap again. Now, theoretically, if I had some elements down here like 500, let's choose some big number, 600, then I would make the comparison and see that this is already the smallest element, so I'm done. So I don't have to go down. I mean, actually, this wouldn't be possible here because we would have some values here, but the idea is that you stop when you have when you are already the smallest value. That's the basic idea. We're going to talk about this more when we implement it. The second idea is what happens when I add a new element. What happens when I add a new element? Let's say, for example, here I have 36 now again, or something like this. And now I add a new element. What happens is I append it to the heap, just at the next free slot. So you can consider the slots to be like this. We have the first one, the second one, the third one, 4, 5, 6, 7, 8, 9, 10. So this is how it's ordered. I'm going to talk about this here, as I said, in a second when we talk about how this works as an array. But basically, you input some element. Let's say, for example, I input the element 23. Or actually, let's go with something that will end up at the top. Let's go with 5. And what I do now is I sift up the element. So now we're not doing a sift down operation. We're doing a sift up operation, also called a swim operation. So we're comparing with the parent node which one is larger, which one is smaller, and then we're replacing them if necessary. So in this case, 5, of course, is smaller than 32, so we replace them. 5 is also smaller than 25, so we swap them. And 5 is also smaller than 20, so we swap them as well. And now we have a valid min-heap again. That's the idea. So for extraction, we take the top, we replace it with the last element, we sift down. For deletion, for insertion, we insert at the end, and then we just sift up until we are at the proper position. Now, how does this work as an array? So how this works as an array is that I have an array with all these values, and the indices are calculated as follows. So the root element is always, or the top element is always the first one. So I have 5. Now the two children of 5 are 20 and 30. So they are the next elements. And the children of 20 now are the next elements. So I would have 25, 40. So these are the children of 20. These are the children of 5. Now the children of 30 are the next in the list. So they would be, this is 50, right? So we would have 50, 36. And then we have the children. So these are the children of 30. And now we have next the children of 25. The children of 25 is just 32. And that's it. So that is our array. Now, instead of just understanding this visually, we can also put this into a formula. So the parent element, or let's start with the left. The left child of a node is the same as saying 2 times the index of the node plus 1. And the right child is 2 times the index of the node plus 2. So if you consider that to be index 0, where do I find the left child of 5? 2 times 0 plus 1, 1. Okay, where do I find the right child? 0 plus 2, 2. Okay, where do I find the right child of this? It's index 2, so it's 2 times 2, which is 4, plus 2, which is 6. So 3, 4, 5, 6, there you go. 36 is the right child of 30, as you can see. This is how you calculate that. The other way around, we could say that the parent of a node, if we want to know that, is the index of the node that we're looking at right now, minus 1, floor divided by 2, if it's not 0. So if the index is not 0. Because then, of course, we don't have a parent node for the first node. But basically, if I want to know, okay, what's the parent node of 50? This is index 5. So what I do is I say 4 divided by 2, 2. So the parent of 50 is 30. That is how we do that. So all of this can be represented in an array, in a simple list. We don't need to work with nodes or anything like that. We can just do index calculations. So that's it for now. Let's get started with the coding, and then we can go and discuss more details as we implement the functionality. So let us go to the current directory, and here now we're going to create a new file called heap.py. So now we're actually going to have just the heap class. We're not going to have nodes. I think this is the first data structure where this is the case. So we're going to implement a min-heap now. Again, I'm not sure if I talked about this, but the max-heap would be the other way around. So we would have 50 at the top, and then we would have values that are less than 50 at the bottom, or below 50. All right, so min-heap. Let us get started with the initialization. The initialization is going to be, so the constructor is going to be just the heap is going to be an empty list. And then we're going to implement the following functions. We're going to have a length function, so a dunder method. We're going to have a representation dunder. We're going to have the method insert, where we're going to be able to insert key and value. By the way, this is something that I didn't mention. All of this that I showed you here is just regarding the key. Every element here that we have can also contain an arbitrary amount of payload or value, we can say. So 5, 20, and so on, these are just the values for the heap to be able to structure the elements, but each of these could have a package attached to them. So here we could have some string hello, for example, attached as a value to this thing. And here we could have some value world attached to this thing. So it doesn't have to be just a value, it can also contain a payload. Which is why we are going to insert key and value, we're going to insert tuples, and we're still going to focus only on the key for the whole operation, but we're going to be able to do that. Then we're going to have the operation peak minimum, which is going to be the same as extracting, but we're not going to actually remove it, so we're just going to show it. So peak min key, or actually, sorry, not key, peak min, and this is going to return the key value pair. Then extract min, which is going to actually do the extraction. It's going to actually remove it from the heap, and then we have to do the sift up, sift down operation. Actually, not sift up. And then we're also going to implement the following methods. We're going to implement Heapify. We're going to implement melt, which is going to be combining the heap with another heap. So we're going to have here other heap as a parameter. And here we're going to actually pass a list. So elements. To summarize this, Heapify will mean we get a list of elements, doesn't have to be sorted, doesn't have to be structured in a certain way, and we take that and structure it so that it becomes a heap, so that we actually get this array structure here that we talked about. And then we're going to have the helper methods that we talked about. We're going to have a parent method, which is going to take an index as input and return the parent index. We're going to have the left helper method, which is going to take an index and give the left child of this index. And we're going to have the right helper method, which is going to do the same thing for the right child. And then the most important methods here are going to be sift up, sift down. So sift up a specific index and sift down a specific index, which are also called, as I said, maybe as a comment here, this is called the swim operation and this is called the sync operation. And as always, don't worry, we're going to talk about the runtime complexities of all these things at the end, but I want to implement them first before we talk about the complexities so you understand how this works. So for the length, it's quite simple. We just return the length of self-heap. That's not too complicated. For the representation, we can also just return the string version of the list. So this is quite easy. We just show the list and that's it. Show the heap, and then you can look at the list. If you want to visualize this as a tree, go ahead and implement the logic to do that. I'm just going to print the heap. And now let us start with the insert method, because that's actually quite simple, even though the logic that makes it more difficult is going to be inside of these methods here. So for the deletion, for the insertion. But remember, all we have to do to insert a new element in a heap is we have to add it to the end, and we have to then sift it up. So we're going to say here self.heap append key value, and then just self.heap sift, sorry, not self.heap, self.sift up this index, which is going to be the length of self.heap minus 1. So remember, for the insertion, all we need to do is append the new element here, and then it's going to not necessarily be at the correct position, sift it up the tree wherever it has to go. And this is always going to be the last element, so length minus 1 is perfect to index it. So the logic will be implemented here in sift up. Peak minimum is also quite simple functionality. All we have to do is we have to say if self.heap, or actually if not self.heap. So if the heap is empty, if we don't have elements, we're going to raise, let's do an index error, because we're going to say empty heap. And otherwise, we just want to get the first element. So just return self.heap 0. That's going to be the minimum element. It's always going to be the root. It's always going to be the top, the first element. Because of that, just return it without doing anything else. For the extract minimum, we can start in the same way, but we have to do it differently because now we're no longer just showing the element. We're not just returning it. We actually have to remove it. We have to extract it from the heap. So we can say min value or min element is equal to self.heap 0. That's the same as before. But instead of just returning it, we now say that the last element of the heap is the self heap, and now the index is again, or actually we can use the pop function here. So either you can access it in the same way by saying length heap minus 1, or you can just use pop. This gives you the last element, so it pops out the last element. If you do it with the index, you have to remove it with the delete keyword or with the del keyword. But with a pop function, you just pop out the last element, you take it, and what we're going to do now is we're going to say if self dot, or actually we don't need to do that because we already checked for that. Or no, we actually have to do that because by popping the element, it could end up being an empty list. So for example, if I have just one element in the heap, which is 10, if I pop it, I could have now an empty list, which means that I need to do it differently. Otherwise, I just remove it, right? And I don't need to do anything. But if I have elements left, so if there is something left in the heap, I need to say that the heap at the first position, the root element, now becomes the last element. And then I want to sift it down. So self.sift down, and then index 0. And in the end, of course, the most important thing, we're going to return the element which we extracted. So again, visually, what are we doing here? We're saying, okay, I'm removing 5 from the list. So from the heap, what am I doing? I'm removing this node and I'm returning it. So here, return 5. But what I need to do now to restore the heap is I take the last element, so 32, and I put it at the top, 32, and then I check, I sift it down. So I compare this again. Okay, this is now 32, this is now 20. Then I replace it also here again. This is now 25, and this is now 32. There you go, heap is restored. So that is what we're going to do. So we're sifting down the element. Insert and extract are going to use that. So let us go ahead and implement these now. But before we do that, let us briefly implement here the parent left and right formulas. These are exactly what I showed you here. So right is 2 times index plus 1. Right is 2 times index plus 2. Left is 2 times index plus 1. And parent is index minus 1 divided by 2. Of course, there are some conditions here. So for example, maybe the node doesn't have a right child. In this case, we would go out of bounds, and we don't want to do that. So we need to return, in this case, none. So we are going to say here for the parent, return index plus 1 floor divided by 2 if the index is not 0. Otherwise, we don't have a parent because that's our root element or top element. For the left, we say return, or actually, let's say left is equal to 2 times index plus 1, which is the formula that we talked about. And now we're going to say return left if left is in the bounds. So if left is less than the length of the heap, otherwise return none. And the same goes for right, just with a different formula. We're going to say here right, and then we're going to say return right, and we're going to say plus 2. So that's that. Now let us implement the sift up. The sift up is just comparing to the parent and moving up if the parent is, if the position is not correct. So if the parent is small, if the parent is larger than me, then I have to move up because I belong further up in the hierarchy to make this a valid heap. So we're going to say here the parent index for the current index that I'm trying to sift up is self._parent, my helper function here, for the current index. And then what I'm going to do is I'm going to say while the parent index is not none, so I'm not reaching the top of the heap, and also, in addition to that, at the index, the key, so index 0, since we're passing tuples. Remember, when we insert key and value. So in order to compare the keys, I need to access the 0th element, so the index 0. If that value is less than the value of its parent, they should swap. So if I'm smaller in a min-heap than my parent, I belong up and the parent belongs down. That is the rule of the heap. So heap parent index 0. If that is the case, so if I have a parent and this parent has a larger value than me, we should swap positions. So I say self heap index and self heap parent index is the same as self heap parent index and self heap index. All right, and the index is then equal to the parent index because what we need to do next is we need to move up and do the same thing. So if I swap positions with my parent, now I'm at the index that my parent was at, so I need to reset this and I need to calculate the next parent index. So the parent index is then self._parent index, and I continue to do that until I'm either no longer smaller than my parent or until I don't have a parent, and then I have the heap property restored. So now let us move on to the sift down operation. Here we need to do the opposite. So we are placed at the top of the heap. So we're assuming we are the smallest element in the heap, which is most likely wrong. And now we're going to find our way down by always replacing ourselves with the smallest child node that we find. So we're going to say here, let's remove this, while true. And what I want to do now is I want to find the smallest index. So it's either going to be me, then I don't have to change anything, or it's going to be one of my children. So either the left one or the right one. I need to know which one it is, and then I need to swap positions with this node. So I'm going to say here, the smallest, I'm going to assume by default I am the smallest. And then I'm going to say that my child is located at self.left index, and my right child is located at self._right index. And then I just need to make the comparison. So first of all, if I do actually have a child, so if actually left is not none, and the key value is actually smaller than the one I have, then I need to swap positions. So if self heap left 0, if that is less than self.heap smallest, which is by default my index, if that is smaller than that, then I need to go ahead and swap the position. So I need to say smallest is now considered to be left, I'm going to swap them in the end, but we're going to say now that the smallest one is located at the index that the left one is located at, and then I can just repeat the same thing for right, and it's going to also compare it to the left child, because if the left child is actually smaller than the parent, then it's also going to be stored in smallest. So I also do that comparison. If right is not none, self heap right 0 is smaller than smallest, then replace this by right. So at the end of this, we're going to always have the smallest variable pointing to the index, or having the index of the smallest node, of the node with the smallest key value. So I need to check if this node is myself. So if smallest is still index, it means that I didn't enter these if statements, which means that we're done. I don't have to change anything. So in this case, just break out of the loop. Otherwise, make the replacement. Heap index should be replaced with smallest. Like this. So we just swap the positions with the smallest element, and then we of course need to progress the index. The index is now smallest, and I repeat the process. So this is again the same idea that we had here. It's just the sifting down. I remove 32, which means 36 is now at the top because I take the last element, and now I sift it down. I look at left and right. Okay, this one is smaller, so I swap the position 36, 20. Then I look left, right. Okay, it's 25, so I swap this with 25, 36. So that is what we're doing here. All right, so that's actually it. Once we break out of the loop, the heap property is restored again, and the only two methods now that we need to implement are Heapify and meld. Now, Heapify again means we take a list of values, we take a collection of values, and we absorb them, we structure them as a heap, and we basically reorder them so that they fit the heap property. This can be done quite easily. What we need to do is we need to say self.heap is equal to list of elements, in case we get any other collection format here. And then we're just going to reverse iterate. We're going to start from the last parent node, and we're going to just sift down all the elements so that we restore the heap property in all the subheaps. And we do that from right to left. So basically from the bottom up, we sift down all the elements. Now the leaf nodes are already obviously trivially valid heaps because they are just a single node, but then we just go from right to left, from bottom to top, and we restore the heap property. So what we're going to do here is we're going to say for I in reversed range, and we're going to go to self underscore parent of a length self heap minus 1 plus 1. And the basic idea here is, again, we go to the last position, the last element that is part of the heap. We go to its parent, so that's going to be the last parent, because that's the first node where it makes sense to even sift down. And then we're just going to call sift down on all these indices. So self sift down I. There you go. And for the meld method now, all we need to do is we need to create a combined heap. So that's not the same as merging, by the way, because I think merging preserves the order. I'm not sure about this, but I think melding just basically throws them together and makes a heap. So the combined heap is going to be equal to self.heap plus other heap. And then we're just going to say self.heapify combined heap. So we're just using the method that we just defined. And one thing that you can optionally do, I think also with merging, what you do is you keep, I think you keep also the other heap existing. And in the case of meld, I think what you do is you say other heap.heap is now an empty list. So you basically really absorb the elements from the other heap. But I think you can implement this however you like, depending on what you want to do with that. So now let us talk about the runtime complexity. This is kind of interesting because we have different runtime complexities here. In a tree-based data structure, again, we're going to be working a lot with logarithms. So for the insertion, obviously we have a heap. In order to just add an element and sift it up, what do we need to do? Well, we do have a heap, and the heap is always going to be balanced. So we don't have anything like in a binary search tree where I can have some linked list-like structure. It doesn't work like that. I'm always going to have a balanced tree because I will never append something not to the next free slot. So I'm always going to have logarithmic time when I'm looking at the height. So in the case of a heap, the O of h is always O of log n. So this is different compared to the binary search tree where we could have imbalances and then we would have to go very long into a direction, and maybe in the worst case we have all of them lined up into one direction, so we have a linked list. In this case this can't happen, so what we need to do in the case of an insert is we just append at the end and then we just compare. We compare how many times height times in the worst case, which means that the worst thing that can happen to me is I append a node at the very end and then I have to shift it all the way up to the top, which would mean I have to go through all the levels, and the levels are logarithmic in terms of n. So the runtime complexity of insert is always O of log n. I mean in the worst case, and not necessarily in the best case. In the best case I just insert and it's fine, so done. But in the worst case I have logarithmic runtime complexity. Now peeking can be done in constant time because I just have to peek at the top element, done. Extracting does not work in constant time because we have the sift down operation. So this works again in logarithmic time. What's the worst thing that can happen? I take the last element at the top or to the top and I have to sift it all the way down to the bottom. Worst case, logarithmic runtime complexity. Heapify, in this case, at least in our implementation here, is linear time because I have to go through all the elements. I mean, not exactly all, I don't consider the leaf nodes, but I have to go through all the elements and perform this, but also each node is sifted down only once in the worst case. So I will not end up in a position where I have to do this worst case runtime complexity, which is, as we talked about, logarithmic. In terms of n, I don't have to do this n times. So it's not going to be n log n because in the worst case, I'm going to always have to only sift down every node once because I'm going from back to front, which means that I won't have the case that I start at the top and go all the way down. This is not going to happen. So this is linear runtime complexity here. The melding also has a linear runtime complexity because all I'm doing here is I'm adding the two lists together and then I'm, heapifying, which has linear runtime complexity. This here can be done in constant time. Obviously, it's just a calculation. Same goes for left, same goes for right. And these, as we already talked about them, in the worst case are logarithmic. And because of that, also insert and delete are logarithmic because I just have to remove. I can extract, of course, in constant time. I can also append in constant time. But the sifting up and down in the worst case can take logarithmic time runtime complexity. So I have to go through the full height, and the height is logarithmic base 2 in terms of n. So that is our implementation. Let's try it out to see if we have some mistakes. I think we always have some small typos or anything like this. So let's see if we have some problems here. For this, what I'm going to do now is I'm going to actually copy paste code that I already have. Because the good thing that we can do here is we can actually compare this with the heap in Python. So actually this was the wrong key. Here now what I have is I have my min-heap and I heapify the following values: 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I just have the same value as the key, doesn't really matter. And I then print what happens when I heapify that, and I compare that with the heapq package or the heapq module in Python, which allows me to do the exact same thing. So if I run this now, I can see I get 1, 2, 3, or actually I get 1, 2, 4, 3, 6, 5, 8, 10, 7, 9. 1, 2, 4, 3, 6, 5, 8, 10, 7, 9. Exactly the same result as the heap package in Python. Only difference is I can also include here a package. So a payload, basically a value. And we can basically do the same thing now with the other methods. So I can compare here what happens when I extract the minimum. I can do the same thing with my heap package here or with the heap module using the heap pop method. So I can run this and we get the same thing. 1, 2, 3, 1, 2, 3. And also I can insert new elements. So I can just, now I need to do this differently. There you go. So I can insert 2 and then print the heap. And there you go. I have, oh, sorry, I saw a mistake here in my parent calculation. It's actually index -1 divided by 2, not +1. This is why my code produced a problem now. So when I try this again, there you go. You can see 2, 4, 5, 6, 9, 10, 8, 7. It's good that we're always testing this because these small mistakes are oftentimes something that's hard to notice while writing the code. And what I can do now as well, this is not something that I can necessarily compare with the heap q module, but what I can do is I can also melt 2 heaps. So I can basically say min-heap 2 equals min-heap, and then I can melt them together. And of course I get a problem. Oh, I think I know what the problem is. I am inserting tuples here. They should be lists. No, this is not the problem. Combined heap is equal to self heap plus other heap. Oh, I think that it's self heap other heap dot heap. There you go. Now it works, and now we have these combined heaps in a single heap. So that is the idea of a heap. Again, this is how you implement a priority queue. You can use this now as a priority queue. You can schedule elements, and then the one with the highest priority, with the lowest value, with the highest rank, you could say, is going to be executed first or extracted first. And of course, you can reverse this. You can make this a max heap by just changing how it works. So you just call this peak max, extract max, and the only difference here is actually that you have to compare for being greater than and not for being less than, and you have to call this largest and not smallest. But the idea is the same. You just want to have the largest values at the top. It's just the other way around. But this is how you implement the heap data structure from scratch in Python. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.